I'll recall a classical result from the model theory, the Keisler's theorem, which says that if we are given a class of first-order models in some fixed signature, it is axiomatizable by possibly infinite set of first-order formulas, if and only if it is closed under elementary equivalence and ultraproducts. The elementary equivalence of two models means that they satisfy the same first-order formulas. And the second item, it is finitely axiomatizable if and only if both K and its complement satisfy this condition. Now, if we pack this theorem into a table, we obtain like this. And one can notice some non-symmetry. We have 3 cells with ultraproduct and 1 empty cell. Why is that so non-symmetric? The thing is that this is not the whole story. Scientists didn't tell you the whole truth. So there are more options for a class, not only axiomatizable, finally axiomatizable, but what else can we imagine? To figure out this, we need to revise the definitions. So for a class, I write K is in L and K is finitely axiomatizable if it is axiomatized by one formula. It is axiomatizable if it is axiomatized by some set of formulas, possibly infinite set. But this can be equivalently rewritten as K is the intersection of some collection of finitely axiomatizable classes. And now, since we have the intersection, let's take the union. I don't have a special name for this collection of classes. And the union of intersection, and possibly so on and so forth. But we don't need so on and so forth because after this, the hierarchy stops. We can show that classes that are representable as unions of intersections are the same classes as those that are representable as intersections of unions, just by distributivity of intersection over union and vice versa. There is an old terminology for these kinds or species of classes, as I say. Finitely axiomatizable classes are also called elementary. Axiomatizable are also called delta elementary. Then we have sigma elementary and delta sigma elementary classes, or sigma delta elementary. It doesn't matter. But nowadays, the terminology is a bit different. Quite often, elementary classes are axiomatizable, not just finitely axiomatizable classes. So I will not refer to this terminology in my talk. So the hierarchy looks as follows. And to get a bit more familiar with these kinds of classes, just some examples. In the first level, finitely axiomatizable are the classes of groups, rings, fields, or partial orders or linear orders. In this room, there are classes of infinite group, infinite rings, algebraically closed fields, and so on. In this room, we have finite groups, rings, fields, and so on. In the upper room, we have infinite fields of finite characteristic, of positive characteristic, of infinite vector spaces of finite dimensions, so a bit mix of finite and infinite. And beyond this hierarchy, there are well-ordered sets, periodic groups, simple groups, and some other. Now, if we look for definability criteria for all 4 kinds of classes, then we obtain a rather symmetric table, all 4 possible combinations of empty cell and ultraproduct. And if we want to get rid of this linguistic relation, which involves the language of first-order logic, and then replace it by some more structural relation, say isomorphism, then we obtain a second table due to Keisler and later to Schelach. Keisler's proof first used the generalized continuum hypothesis. Schelach succeeded to avoid it. So again, we see the symmetric, all 4 possible combinations of ultraproduct and ultrapower. And the main reason for this symmetry is that the first order language and models respect negation, or I would say negation can be internalized. If the formula is not true in a model, this can be expressed equivalently as some other formula, namely the negation, is true in the model. Not all languages and structures satisfy this condition. And this makes difficulties for finding similar criteria of definability. Now let's switch to the model language. We have the usual model formulas using Boolean connectives and the box operator. We will consider only Kripke semantics, although other possibilities are, of course, possible. And here's the usual definition of the truth of a model formula in a point of a model. So formulas are evaluated in pointed models, a model with a point. And of course, there is a definition, there is a notion of a formula being true in a model, in the entire model. There are natural relations between models or pointed models. The first is the modal equivalence. Two models are modally equivalent if they satisfy the same formulas. By simulation, this is a more structural relation. It is a binary relation between worlds of two models that respects the valuations of variables, and each step in one model can be simulated by a step in another model into the corresponding point, and vice versa. And if we want to relate two models, not pointed models, then we come to the notion of global bisimulation, which covers the whole model M and the whole model N. Two key notions related to these semantics. If K is the class of pointed models, almost the same is applicable to classes of models. We call it this class modally compact if, I would say, the compactness principles holds for this class, if we confine to this class. So for every set of formulas gamma, if every finite subset is satisfiable in K, then the whole set gamma is satisfiable in K. Examples are classes of models or pointed models that are definable by a single model formula, by a set of model formulas, or even by a set of first-order formulas. All they are modally compact. Another important notion is the class, what we introduced, the class of modally saturated. A class is called modally saturated if every pointed model in it can be saturated. For every pointed model in it, we can find another pointed model in this class, which is elementarily in a model equivalent to the original one, and the new model is modally saturated. I will not give the definition of modally saturated model. It is a bit more technical, but you can find it in the textbooks. I will just give two facts that we need about it. First, the relationship between bisimulation and model equivalence. In general, we have only one implication. If two structures, two pointed models are bisimilar, then they are model equivalent. But for saturated models, the converse implication also holds. In general, it doesn't hold. So, a saturated class is the class in which we can saturate every pointed model, or the same can be done for models. And in these terms, we can formulate a general result. A bunch of definability criteria formulated in terms of model equivalence and compactness. For instance, a class of pointed models, again, I'm considering pointed models right now, it is finitely axiomatizable by some formula, model formula, if and only if it is closed under model equivalence, it is compact, and its complement is compact. And you can read similarly all 4 lines. And if we, again, want to get rid of linguistic relation and replace it by some structural relation, by simulation relation, then we can do this at the price of adding the saturatedness condition at every cell. So this is a general result, and it is applicable to a wide range of model languages, in fact, not to the basic model language with one box. And therefore, we can obtain as a consequence many known definability criterion for basic model language, for tense language. I'm not sure if there is a author of this theorem before. The language of the model language with the universal modality, graded model language, all these results were considered before, and but now we can obtain them from a single general result. And if we want to get rid of linguistic relations in favor of bisimulation relation, the corresponding bisimulation relation for each particular language, then we can do this again at the price of adding ultra power at every empty cell. Ida Venema asked the following question. Look, we are searching for definability criteria, and we obtained a lot of them, but they use the operation, the ultra-product operation, and ultra power as a special case, which was designed firstly for the first order logic. It is not purely model operation. It preserves not only the truth of model formulas, but also the truth of arbitrary first order formulas. But can we do the same? Can we achieve the same goal with purely model operations? We have some operations in model model theory. For instance, the ultra filter extension. Given a Kripke model, we can obtain a model whose worlds are all ultra filters over the original set W, and some particular relation and valuation. This new model is model equivalent to the original one, so the operation preserves model formulas, and moreover, this new model is saturated. I didn't write it here. This is the operation for models. If we want to consider pointed models, there were no such an operation before Ida Venema discovered this. He didn't give a special name. I call it ultra union of a class of pointed models, of a family of pointed models. So first we take the disjoint union, then ultra extension, and we also need a fixed point, some distinguished point in this model, an ultra filter. This can be taken as arbitrary ultra filter that contains all cofinite sets of this set, subsets of this set. And this new operation, in fact, it is not, strictly speaking, an operation. It is non-deterministic. This alpha can be taken in many different ways. But this non-deterministic operation behaves much like the usual ultra product. And he succeeded in 1999 at the conference devoted to 50th birthday of Van Bentham to give all four criteria. In fact, he considered only the last two lines, but the first are obtained very easily from the last ones. And again, we can switch to bisimulation at the price of now of adding ultra extension. So ultra extension this time works like ultra power in our previous tables. And ultra extension makes the model saturated, and this ultra union makes the models, the pointed models, the classes of pointed models compact. Of course, we can do the same, for instance, for tense language. Up to now, we were talking only about classes of pointed models, models with point, which respect negation. A formula is not true in a pointed model if and only if its negation is true in that model, in that pointed model. If we now want to consider definability of classes of models, then we no longer have this property, and this makes some difficulties. One difficulty is the surprising fact that if we want to formulate again, in abstract way, our criteria, then the whole last column contains the compactness. So this last column doesn't allow us to differentiate between different lines in this table. And the information in the first column is not sufficient to differentiate either. So in this table, only line 1 and 3, which are marked by the check mark, are theorems, and the other are just copied from the first and the third. And information in them is not enough to give the criteria. So the question is open. And again, if we switch to bisimulation, again, we add saturatedness in every cell, but again, only line 1 and line 3 are obtained, and while the other two lines are not the complete criteria. Nevertheless, if we formulate the criteria in terms of ultraproduct, if we use the ultraproduct operation to give the criteria, then we can find all the criteria for all 4 lines. This looks like this. Again, symmetric, except for this ingredient. This is the generated submodel relation. One model is a generated submodel of another one. So the class K should be closed under taking generated submodels. And this is the disjoint union operation, which is available if we consider models, not pointed models. And again, if we switch to bisimulation, this time global bisimulation, which relates models, not pointed models, we can do this at the price of adding ultra power at every empty place in our table. But if following Evgeny we want to obtain purely model criteria that don't use ultraproduct, but some operations modally are intrinsic, so that are specific to model language, then not all lines will be completed. We have Evgeny obtained the criteria for model definability by an arbitrary set of model formulas for a class of models. We added the first line, but the second and the fourth are open questions. So in particular, we do not know any operation or relation which is purely model that can be distinguished between classes of definable by a set of model formulas and one model formula. For every known operation, purely model operation, either both of them satisfy the closure condition or not. So this is a kind of open question again. And as a last example, if we consider the model language with universal modality, and again, we are now considering classes of models, not pointed models, then we are happy because we can internalize negation now. A model does not satisfy some formula, we can express it in the model language with the universal modality, if and only if in this model the formula not universal modality phi holds. So the symmetry is again with us, and we obtain easily criteria for all 4 lines for the model language with the universal modality and for the classes of models. But these criteria use ultraproduct, non-model operation. So the open question is, can we do this purely model in terms of Evgeny? Okay, to conclude, there are obvious further directions that can be pursued. Firstly, we considered only Kripke semantics. There are other important semantics for model logic, for instance, neighborhood semantics, topological semantics, algebraic semantics. We can do the same tasks for other languages. For instance, for intuitionistic propositional language. It also has Kripke semantics, and moreover, some results are already obtained by Robert Goldblatt and Piet Rodenburg in 2005, and 1986, correspondingly. We can add new modalities. Well, I mentioned already inequality and some open question related to it. We can add transitive closure or nominals or some other logics that involve transitive closure, say PDL or CTL, and so on. We can consider infinitary model language, either with the countable conjunction and disjunction or arbitrary conjunction and disjunction. And in this latter case, so for any set of formulas, conjunction phi is a formula. In this case, we need to revise our basic definitions of our hierarchy. We have classes definable by a single formula. Classes definable by a set of formula are the same because a set of formulas can be converted into a single formula. So the second layer will be the classes definable by a class of infinitary formulas, which is quite unusual. So we expect some interesting results here. And for instance, modal intersystem and intersystem predicate logics, for them all these questions are also meaningful. And another important direction is what will be if we confine ourselves only to finite models. For instance, we have a Van Bentham theorem that follows easily from our tables. First, the formula is equivalent to a model formula if and only if it is invariant under bisimulation. This holds in the setting of arbitrary models and in the setting of finite models. And the proof for finite models uses very different technique. We have no longer compactness, and we need to devise new technique. So this is a rather interesting and important direction. So, and before I finish, I would like to congratulate Lev again. Thank you.
Thank you very much for the nice picture and for an interesting talk. Are there questions? So please.
So you considered model definability and pointed model definability,
yes,
right?
Yes.
But usually we are interested in the like transitivity or reflexivity or well-foundedness. It's they are property of frames rather than models. And can you say something about
this is another direction in which quite a lot of results are obtained. But in fact, they usually obtain, well, let me show on this slide, they usually obtain results for this third line.
Yes.
Like Galbraith-Thompson theorem, a class is modally definable by possibly infinite set of model formulas if and only if some conditions hold. Moreover, these results are usually restricted to elementary classes, not to arbitrary classes. And results of this kind are obtained for several model languages, but I'm not aware of any results for other lines, in particular for the basic model language. This last line is an open problem. We are not aware of any, does there exist a class, an elementary class defined by a set of first order formulas that is definable by a set of model formulas, but not by a single model formula. And therefore, so not even a single example of this distinction, let alone any criteria for the last line.
Even though you don't have any such general result, do you know any particular interesting?
Not really, because
usually we are interested in schema, axiom schema, not single axiom in the modal case, right? So.
Yes, yes. The thing is that when we switch from models or pointed models to frames or pointed frames, we are in the realm of second order language in which we don't have really the compactness, and therefore many results and technique fail to go. So, but so there are some interesting open questions there, and some results could be done, but there is no complete picture like here for models.
Yes, but the question definitely makes sense, right?
Yes,
so that
yes,
makes
really.
it even more interesting. More questions from the audience? Yes? Denis?
Thanks, Lev. Are there some known results in this kind in predicate model logic?
I didn't check, but I don't remember any. Maybe there are, but I didn't. I was not very interested in predicate logics.
Okay.